Dear students, let's learn more about this chapter, electric potential. So we have a term called capacity of a conductor. Now to understand this, let me take example of a sphere. So this is a spherical conductor having a radius r. Right now the potential is 0 because there are no charges over it. If I provide some charges to it, then its potential becomes V is equal to 1 by 4 pi epsilon naught Q by R. This is expression for potential on the surface of a sphere. So if I give more and more charges, Q increases, V also increases, so that we can write V is directly proportional to Q, or Q is directly proportional to V, with a proportionality constant denoted by C into V, and the C is called capacity of a conductor or capacitance of a conductor. So if I have to rearrange this for C, then C is equal to Q by V. So this is a very important basic formula. So what is the meaning of capacity of a conductor? Ability of the conductor to hold the charges, to store the charges is called as the capacity of a conductor. Ability. But can we give any amount of the charges? No, because once it attains certain amount of the charges, it overflows, or it's get leaked to the surrounding. So something like this, here we have a beaker, and so just see what's exactly given. Right now there is a beaker, big beaker, and inside there is a small beaker, and as the liquid is filled, you can see it overflows, correct? So its capacity is fixed. Beyond that it cannot hold any amount of the liquid. And another interesting factor is that here, see, once it is filled, you cannot see the inner beaker there. Okay, so that's because of the same refractive index of the glass as well as that of the beaker. So some optics also involved in this particular animation. Okay, so see, that is the meaning. So their capacity means the ability to hold the liquid in a beaker. Here capacity means the ability to store charges on a conductor. So what is the definition of the capacity of a conductor? Capacity of a conductor is defined as the ratio of the charge acquired by the conductor to the increase in its potential. If it attains more charges, potential becomes more, so that the ratio remains constant, and that constant is called capacity of a conductor. So what is the mathematical form? The mathematical form is this: C is equal to Q by V. Remember, very important. What is the SI unit of it? Q is measured, it's a charge measured in terms of coulomb. V is a potential difference measured in terms of volt. So it's a coulomb per volt is the unit, but for which we have a basic unit called farad, which is a symbol is F. So 1 farad is equal to 1 coulomb by 1 volt. So farad, that's named after Michael Faraday. So farad is the SI unit of capacitance, which is equal to 1 coulomb per 1 volt. What are the factors on which it depends? What are the factors on which capacity of a conductor depends? Now tell me, what are the factors on which capacity of a beaker depends? It depends on the size of the beaker. Greater the size of the beaker, more its ability to hold the liquid. Same thing here. So the first factor is, it depends on the size and shape of the conductor. Okay. The second factor, it depends on the dielectric medium surrounding the conductor. Okay. And the third factor is that it depends on the presence of other conductor. Presence of other conductor. So these are the three factors on which capacity of a conductor depends. Okay. Now, what exactly a capacitor? Now, in the case of capacitor, we have two conductors, not one, there are two conductors. So if I am going to consider a conductor in the shape of a plate like this. Okay, so two such plates. Now, if I take two such plates with a medium in between, then we have a lot of advantages. So, instead of taking a single conductor, we take two conductors, or we can have two spherical conductors like this, or we can have two coaxial cylinders like this. Okay. So, this kind of arrangement is called as a capacitor. So, a capacitor is a device in which two conductors are separated by some distance and that space is filled with a dielectric medium. Now, this is called parallel plate capacitor. This is called spherical capacitor. This is called cylindrical capacitor. So, in a capacitor there are always a minimum two conductors are there, not a single conductor. If it is a single, we just call it as a conductor, we do not call it as a capacitor. To call it as a capacitor, there has to be an arrangement of minimum two conductors with a gap, and that space is always filled with a dielectric medium. Okay, so the space is filled with a dielectric medium. So, one such capacitor, you must have seen, a lot of circuits, they consist of this kind of a device. Now, this is a capacitor, this is called electrolyte capacitor, and for every capacitor you can see there are two terminals are there, two, okay, like this. So, for 1 and this is 2 like this, 1 and 2, 1 and 2 like this. Okay. So, for both the conductors there are terminals so that we can connect them in the circuit. So, this is the diagram of electrolyte capacitor. So, what is a capacitor? Capacitor is a device in which we can store charge as well as energy. Okay. So, how to store charge, how to store energy, so that I am going to explain later, but that is the advantage of the device called a capacitor. Highly used device in almost every electrical circuit or every circuits which we use, home appliances which we are going to use, you will find this particular device in various sizes. Some circuit may contain a very small capacitor, in some there may be big capacitor. So, highly used device called capacitor. So, what is a capacitor? Device which is used to store charge and energy. And we are going to learn about a type of capacitor which is parallel plate capacitor. In parallel plate capacitor, there are two parallel plates. Both the plates are of the same shape. Both are rectangular, both are spherical, or both are square, identical, okay, separated by some distance. So, something like this. Okay. So, this is the first plate, this is the second plate, and these plates are connected to a battery so that we can charge them. So, that once you connect this will attain a positive charge which is given plus Q. This will attain a negative charge, so that will be minus Q. So, you can draw them here inward, inside, like this. So, what this indicates is connecting to the earth. Earth has a zero potential, or in simple it also represents that this particular plate is at lower potential. Small d is the separation between the plates. Small d is the separation between the plates. So, let us derive an expression for capacity of a parallel plate capacitor. So, what are the variables? First, Q is the charge on each plate. Capital A is the area of the plate, so that we can find the surface density of the charge on each plate. It is a charge per unit area, Q by A. So, that is one of the equations. And when you consider two plates like this, here, every plate produces an electric field which is given by E is equal to sigma by 2 epsilon naught. Now this is the electric field produced by each plate. So I'm going to take a point outside and then I'm going to take a point inside. At a point outside here, electric field due to this positively charged plate is away from it. That's because it's a positively charged plate and the value is given by E is equal to sigma by 2 epsilon naught. At the same point, due to the negative charge, it will be towards that. So that will be again E is equal to sigma by 2 epsilon naught. And they are equal. So the angle between them is 180 degree. So therefore, what is the electric field at a point outside? It's given by E is equal to sigma by 2 epsilon naught minus sigma by 2 epsilon naught. That becomes 0. So field is 0 outside the plates. So that's what we learn. What about at a point inside? Here, due to the positive charge, it's away from it. That means towards my right. Due to the negative charge, towards the negative plate, again towards the right only. Now, what is the electric field in between? It's E is equal to sigma by 2 epsilon naught plus sigma by 2 epsilon naught. What is the plus? Because both the vectors are in the same direction. So here the vectors will get cancel each other, here the vectors will get added up. So therefore, now that's equal to sigma by 2 epsilon naught plus sigma by 2 epsilon naught is nothing but sigma by epsilon naught. Add them. Half plus half is 1. But what is sigma from here? Sigma is Q by A. So we get Q by A epsilon naught. So this is the electric field between the plates. There is a potential difference between the plates which is given by E into D. Potential difference is equal to electric field into the distance which is D. Electric field is here Q by A epsilon naught. So that's why Q D by A epsilon naught. Now this is the potential difference. So the final step is we want to find the capacitance. Capacitance is given by the ratio of the charge on either plates, which is Q by the potential difference, which is Q by potential difference is this QD by A epsilon naught. QQ will get cancelled, and what you get here is A epsilon naught by D. C is equal to A epsilon naught by D. So therefore, finally we have derived an expression for capacity of a parallel plate capacitor. Now this is the expression for capacity of the parallel plate capacitor. If the space between the plates consists of air as the medium. Okay. Now suppose if there is a dielectric medium having dielectric constant epsilon r, then this equation changes to Cm. I will write this, I will write it as Ca. Cm stands for capacity in a medium. Then it becomes A epsilon naught epsilon r by D. See the difference. So these two equations are important. This is if the surrounding medium is not the surrounding, the space between the plates is air. If there is some dielectric medium, then it is given by A epsilon naught epsilon r by D. So that is the difference between the two equations. So let me write the two equations here. So capacity of the capacitor with air as the medium in between is given by Ca is equal to A epsilon naught by D, and in a medium Cm is equal to A epsilon naught epsilon r by D. So these are the two important expressions based on which we are going to solve numericals later. So this derivation has appeared once in the exam, March 2015. So that's why this is an important derivation. So hope you have understood the derivation. So next, define dielectric constant in terms of capacity of parallel plate capacitor. Okay. So question that has appeared in this year, September, that's in the supplementary exam. So here we have the two equations. One, capacity of the parallel plate capacitor with air as the medium, and here we have a capacity of the same capacitor in a dielectric medium. I'm going to divide this equation, Cm by Ca. Cm by Ca is equal to A epsilon naught epsilon r by D into we have to divide this, so this goes to the numerator, d by A epsilon naught. This A epsilon naught will get cancelled, d will get cancelled, and we will get this equation, epsilon r is equal to Cm by Ca. So based on this I can define. How to define dielectric constant? Dielectric constant of a medium is defined as the ratio of capacity of a capacitor with the medium as a dielectric to the capacity of the same capacitor with the air as a dielectric. Understood this? Dielectric constant of a medium is defined as the ratio of capacity of a capacitor with medium as dielectric to the capacity of the same capacitor with air as dielectric. So that is how we can define we can define dielectric constant of a medium in terms of the capacity of parallel plate capacitor. So this is another important equation. So that is we can write epsilon r is equal to Cm by Ca. So this is the third one. So this is the first equation, this is the second one, and that is the third equation. So let's see more question from the exam. The question is, on what factors does the capacity of parallel plate capacitor depends? On what factors? So there are three factors are there. The factor number 1 is A, the factor number 2 is epsilon r, the factor number 3 is a d. So what are the three factors on which it depends? It depends on the area of the plates, distance between the plates, dielectric medium between the plates. What are the three factors? First one, area of the plates, distance between the plates, and the other dielectric medium between the plates. So these are the three factors. Again, important question, repeatedly asked. Let's see one more question. The question is, a parallel plate capacitor with air between the plates has a capacitance C. What will be the capacitance if the distance between the plates is doubled? Capacitance is always given by C is equal to A epsilon naught epsilon r by d. C is inversely proportional to d. So when this is doubled, capacitance is halved. Correct? When this is doubled, you can see for capacitance this is equal to half, right? So when d is doubled, capacitance is halved. So that's why the answer is C by 2 is the answer. So hope you have understood that answer. Because C is inversely proportional to d, when d is doubled, capacitance is half. So initial capacitance is C, therefore the new capacitance is C by 2 is the answer to this particular option A. So option B, the space between the plates is filled with a substance of dielectric constant 5. So the value of, so answer to the first question is C by 2. So just now I had given an equation, epsilon r is equal to Cm by Ca. The value of epsilon r is given 5. We have to find this capacitance Cm, the new capacitance we need to find. The initial capacitance is given as C. So therefore Cm is equal to 5C is the answer. Therefore to this the answer is 5C is the answer. So again, question from this here for 2 marks question, applications, type of question. So hope you have understood how to answer this particular question. Also, if they ask how to increase the capacity of a parallel plate capacitor, how to increase? There are 3 methods by which we can increase. One, by increasing the area of the plates, by using a medium of higher dielectric constant, and the other is by decreasing the distance between the plates. By decreasing the distance, we can increase the capacitance because it's inversely proportional. By increasing the area of the plates, we can increase the capacity. By using a medium of higher dielectric constant, we can increase the capacity of the capacitor. So, hope you have understood the concept of capacity as well as a capacitor. Capacity is always defined when we say capacity of a conductor, it is for a single conductor. When we say capacity of a capacitor, means it is an arrangement where there are two conductors are there separated by some distance with a space filled with a dielectric constant. So, that kind of arrangement is called as a capacitor. So, let us learn more about this topic in the next class, and just a reminder that this Sunday I will be conducting the test, and on Saturday we will have one interactive session on Zoom app. So, download the app well in advance, and I am going to provide the link just 5 to 10 minutes prior to the meeting. So, all that detail will be given in our group. Okay. So, start reading only one chapter. In that, one of the portion is deleted already, and I have already excluded from the study material, and then I have already uploaded the new study material. So, study and try to score well in the exam. So, all the best.